I am Mark Hughes, and I am here representing Royal Circuit Solutions and Advanced Assembly. Royal Circuit Solutions is based in Hollister, California, and we also have a flex shop in Santa Fe Springs. Advanced Assembly is in Aurora, Colorado, and combined, well, not combined, separately, we have over 15 years of experience at each shop, and we're proud to be the original quick-term PCB fabrication industry leaders. Whenever you want your PCB, we can deliver it to you. And that includes, for some customers, same-day turns. For some customers, we've built complex boards in as little as 4 to 6 hours. So when you need it, give us a call. We'll make it happen. I'd like to thank everyone for taking time out of your busy day to join us for the webinar. For your convenience, we will record the webinar and post it on our YouTube channel. We often get asked by our customers, how do you do high-speed design? So we just put together a little webinar. It's certainly not a full course on high-speed design by any measure, but it might give you a few things to think about and at least give you a place to start asking us questions, and we can have a back and forth with you. As we go along, please ask all questions in the question and answer box, and we'll either answer them live or we'll hold them to the end. Nope, I don't have an animation of that. Sorry about that. Well, my name's Mark Hughes, and I am the research director over at Royal Circuits and Advanced Assembly. My job is to bring you informative content. If you have any questions ever, you can reach me at mhughes@royalcircuits.com or mhughes@aapcb.com. All right, we're talking about high speed. Who needs high speed? Well, as my friend Dr. Eric Bogatin often says, if you can build a board and it looks like this, you don't need to worry about it. You can make pretty much any printed circuit board design and it's going to work, right? But this is based on last generation technology, when the edge rates weren't quite so high, when things weren't moving quite so fast. With each generation, printed circuit board designers are able to make those transitions happen faster, and that can make some bad things happen. So even if you're designing boards like the one that you see on the screen today, that looks like something I might have built when I was in college, 25, 30 years. No, how long? I don't know. Let's call it 25 years. You might not be able to build that tomorrow. Those chips might not exist, or those same chips in the same packages might have different edge rates, and it doesn't work anymore for you, and you start running into troubles. And that's when you start looking a little more into high-speed design. So what is high speed? Well, any transition, either from logic low to logic high or logic high to logic low, it transitions over some certain amount of time. And usually, not always, but usually what we do is measure the difference between a 10% of the full transition and 90% of the full transition, a 10-90, and measure the time it takes for that to happen. And depending on how short of a time interval that is, that can depend on what you're going to have to do to your board. Okay, it doesn't really matter what clock frequency you're running at. You could have a 10 kilohertz, you could have a 10 gigahertz, and you could have some of the same problems. So what you really want to look at is the edge rate, the time it takes to go from 10 to 90 or 20 to 80% of the signal value. And another one of my friends, Mr. Rick Hartley, over at PCB West, went through the polar and plotted a bunch of different points for a bunch of different values for a dielectric with a dielectric value of 4.1. And he came up with values. I just plotted them. I didn't want to pull out the individual points, so I just fit a line to them and plotted it out there for inner and outer. And he said, if you've got like a 1 nanosecond rise time, you really don't need to start worrying about things till you're about 10 inches long. If you've got a 100 picosecond rise time, you really don't have to worry about things until your traces are 1 inch long. Okay, well, that can happen pretty easily on a board. And if you're down into the tens of picosecond rise times, I mean, you can't even get out of the connector hardly without having to worry about what's happening on your board. Now, last gen stuff is usually this or higher. So you've gotten away with it. I mean, unless your traces are 100 inches long, you don't really need to worry about what's going on. But as we start moving left on this curve, as the rise time intervals decrease, the length of the trace that you can have is going to continue to decrease in length. And when you get so short that you actually are able to have this signal rise a full level before it's able to completely traverse the trace, that's when you get into trouble. So my friend Eric Bogatin has a rule of thumb that basically just says whenever your rise time in nanoseconds is greater than your length in inches, you need to pay attention to what you're doing in your board. So that's this line that I plotted right down here. When your rise time in nanoseconds is greater than the length in inches, you need to worry about it. And if you'll take a look at Mr. Rick Hartley's number, and again, he did this with an EM field solver with the software Polar, he almost allows you to squeeze another order of magnitude out of what you're doing. But it's still a good rule of thumb because it's very easy to remember. So anything more than that, you might need to even simulate your board to see what's going on. All right, so what's happening? Well, and if somebody could tell me, is this animation displaying on your screens? It's static on mine, if somebody doesn't mind throwing something up in the chat bar. But what I'm trying to show here is that anytime that you have a wire, a conductor, and you change the electric potential on either side of that conductor, charges are going to start flowing inside the conductor. And when they do, they're going to start affecting the electromagnetic field that surrounds the conductor. So take a second to kind of let that soak in. You've got an electric field that goes out radially and a magnetic field that encircles the conductor. Took me a little while to make this one, I'm not going to lie. Thank you for your comments, by the way. I appreciate it. The field affects what's happening inside the conductor, and what's happening inside the conductor affects what's happening in the field. And the rate at which that happens, the rate at which those things two influence each other, the speed of causality is often referred to as the speed of light. Well, that works in vacuums and open spaces, but when you're inside a dielectric, it's going to be some fraction of the speed of light. So again, the conductor affects the field affects the conductor. So what happens though is sometimes when you exceed that speed of causality, when you get changes happening in your conductor so fast that the field isn't able to return energy into that conductor, right? You put a potential difference on the conductor, things start moving around and affecting the field. Well, if things happen slow enough, the energy can be returned to the field, or from the field into the conductor. But oftentimes we have these changes happening so quickly that the energy can't get back into the conductor, and it ends up getting radiated out into space. So here's an animation I made a couple years back. It's actually of an antenna of a Hertzian dipole, and I happened to have it handy. Didn't take a whole lot of time to make, is one of the reasons I chose it. But the other one is to impress upon you the fact that if you're not careful with what you're doing in your high-speed design, you are going to be making an antenna, and those are bad. And it seems like my animation stopped. There we go. A lot of people, when you're thinking about antennas, people always look at the far field, what's happening far off in the distance. And that can happen too. You can radiate the energy away. But what you really need to worry about in high-speed design is what's happening in the near field. That little area up before, where you see this stuff start snapping off. It's really the interesting place, because that's the part where you can return energy to the conductor, or you can return the energy into a return path. But if you don't do something with that energy, it is going to radiate off into space, and it will eventually find some other copper in your circuit or some other copper somewhere out in the environment and wreak havoc. So anyhow, hope you guys like that one. Anyhow, you always need to plot a return path so that the energy that comes out of that conductor and goes into the field that surrounds the conductor, that it has a path to be absorbed, a path to go back. Otherwise, it's going to find one, and bad things are going to happen. Excuse me. Another way to look at this thing, as a change is propagating along the length of a conductor, there's going to be some inductive coupling and there's going to be some capacitive coupling to nearby conductors. And as a current starts moving through a conductor, it's going to cause a return current to start flowing in the other direction, in nearby conductors. This is called essentially crosstalk. This can be negative interference that adversely affects your circuit if you're not careful. And there's two typical types of crosstalk, one due to the capacitive coupling and one due to the inductive coupling. So maybe I should go back here for just a second. Right, the inductors wrap circumferentially around, the magnetic field wraps circumferentially, I can't say it, circumferentially around a conductor, and the electric field is radial, so it would be creating field lines in between. And the longer that you allow two conductors to be side by side, to be near each other, the more that you can affect that second conductor. Capacitive coupling, in here I have it shown as kind of like this filled in green area. Capacitive coupling is something that happens almost immediately, right? It's going to reach a peak within, like half the rise time. It happens very quick. The good news is that the voltage level is, relatively low, but it can still transfer energy from one trace into another if you keep these things too close to each other. And it will also affect both the near end and the far end as far as crosstalk goes. Inductive coupling can be a bigger pain in the butt because the values can become as high as the original signal. But the good news is inductive coupling doesn't happen too much on interior layers. It gets attenuated far too quickly. So as long as you take your traces inside the board, this big one isn't as big of a problem. The green one, the capacitive coupling, will happen, and it's proportional to how long you let two conductors be in proximity to each other. So if they're in the same part of the board for, a couple of millimeters, a couple inches, okay, it's a big deal. Maybe, maybe not, depends on your rise times. But if you run these things side by side for 6 inches, you probably got a problem. And here is an example, if we take a look at the graphic, of some of that crosstalk. This is off of some Beagle Bone Black, if memory serves. So here we've got a switching signal in cyan on channel 2, and you can see quite a bit of ringing, quite a bit of reflection that's coming off on each transition. And if you look down onto the yellow signal, which is a different data line, you can see that that energy was coupled to that second line. Now, the question is it big enough to be a problem? Well, you've got to kind of decide that depending on your logic levels and your noise margins and all that. But Dr. Eric Bogatin, another rule of thumb, says try to keep the noise voltage less than 15% of the signal voltage. That's kind of what you can aim for. And you can determine how much noise voltage is going to be induced given this handy-dandy equation from his latest book, Bogatin's Practical Guide to Transmission Lines, if you guys want to check that out. But again, the longer that you keep two conductors near each other, the more of a disturbance that you can expect to see. And if these conductors were next to each other longer, we would expect the noise margins to probably be higher. Just depends at what time, how long these things are together. All right, next, handy dandy graphic. Ain't that pretty? So what we're looking at here is a graphic that has a top piece of copper, 3 strip lines, dielectric or core, another strip line, and then more dielectric, and then a bottom piece of copper. And we're going to take a look at what happens when you have conductors side by side versus one over the other as it relates to differential pairs. One thing to note before we go on, differential pairs need return paths. And I'll say that again, differential pairs, each one of those conductors needs a return path. A lot of people forget that fact. They'll put two next to each other and they'll assume that, you know, the fields of one cancel out the fields of the other. And that is simply not the case. It works pretty well if you're talking about HDMI cords or Cat6 internet or something like that. But really what these things are doing are providing two copies of the same signal, and they do to some extent confine the electromagnetic fields between the two conductors. But they don't always stay in phase. It's not always perfectly one is lined up with the other. As these things travel over different dielectrics and different epoxy resins, and as the space changes, as these things are compressed, you know, when we put them in the high pressure presses, I made these graphics wavy because, and they are exaggerated a bit, but that's what happens when these things go in the presses. They don't come out all perfectly flat and smooth and whatnot. They come out, you know, ruffled and bumped. I mean, they're still relatively flat, and I'm not talking about, you know, more than a mil or two, but it's enough to change the impedance, which is enough to slow one of these things down, which is enough to make, you know, one transition not at the exact same spot in space as the other one. So you can't expect these things to cancel each other out. Even if they did, they would get out of sync. So you always have to provide a nearby return path for these. And just another graphic of even and odd mode. If, you know, if we did have a truly differential pair and one was going one way and one was going the other, okay, that'd be one thing, but it never happens that way. These things get out of sync almost immediately after they start to travel. So anyways, put in a return path. And while we're at it, don't forget about return paths for your ground returns, right? If you're transitioning from an outer layer to an inner layer to out, whatever, maybe you remember to put in the copper above or below the strip line. But did you think about what's happening when that trace goes vertical in that via? Did you give a path for that to go? Hopefully you did. A lot of people forget to. I mean, if you can, put in four vias on either side of a differential pair, you know, two for each trace. If you can't, at least put in one. But you need something for the energy to couple back from the trace back to the ground via. All right, so two types of strip lines. And by the way, for the uninitiated, strip lines are inside boards and micro strip lines are on the outer layers of boards. Anyhow, two types of them that are pretty common are the edge coupled and broadside coupled. With edge coupled, the strip lines are on the same plane, and we can usually, from a manufacturing standpoint, we can usually control the impedance quite well on those types. Next type is broadside couple. So these things would be on either side of a core or a prepreg. Now, the good news with these is you can often fit more broadside coupled inside a board. You can put more next to each other. And the other good thing is that these things are more immune to noise than the edge coupled, and we'll get into that in just a second as to why. The bad news is it's a little harder to control the impedance on the broadside coupled. Just going back to my image here, you know, you push things in these high pressure presses, things move around, things shift. It becomes a little more difficult. It's going to depend on the resin content, you know, how much, it's going to depend on a lot of things. So when you've got two on top of each other, it is going to be better signal integrity. I'm not signal integrity, better noise immunity. You can also fit more in, but you might have a lower yield. And the reason for it is this. Let's say that we've got a signal coming down these two, and the blue trace that's highlighted ends up being the aggressor. That's the one with the mean signal on it that's going to bleed into the other two. Well, the other two traces are relatively the same distance away. So any signal that gets deposited into the, you know, any energy that goes into these two traces, it's going to be roughly the same amount of energy. So then it can be canceled out on the other end. All right. What happens if we flip that around? What if one of these red ones is the aggressor? Well, if you look at it this way, the second trace is so much further away. The energy of these, depending if you're looking at magnetic or electric, either dies off with the cube or the square of the distance away from the aggressor line. Okay, well, I mean, granted, these two are kind of designed a little too close, but the second one is so much further away. So you're going to get a much stronger signal on the first line than the second one. So they're not going to cancel. So if you do have to run two strip lines next to each other, you're better off with the broadside coupled than with the edge coupled, just based on a basically distance, right? So going back here, the victims are both roughly the same distance away, within a margin. Here, not even close. You're going to get significantly more energy coupled into the center blue line than you are the far one. So with that, any questions on that before I go on? Because it's going to kind of jump a little bit. You can feel free to ask them now in the Q&A. No. All right, I'm boring you. Perfect. All right, other things you need to worry about when you're doing high speed. The next thing that I thought you might need to know about is the idea of ground bounce. Integrated circuits live on these silicone dies that are tied to the exterior pads with bond wires. Then, the bond wires are tied to the circuit board with solder, and then the solder goes into the LAN pad, then the LAN pad goes into the planes, and then the planes go over and they connect to some power source, then we circle back around. What you end up with is a big fat loop. Conductive loops are, can have high inductance. And the change in voltage in a loop is proportional to the inductance by times the change in current over the change in time. Well, the issue that we have now isn't that there's big currents, but these DTs are getting so dang small, 100 picoseconds, 50 picoseconds. That means that you can generate a substantial change in potential, substantial potential difference. So where does that exist? Well, it exists between the die and the reference plane. You can actually very easily generate a very large voltage between these two places. So if this is if 0 volts here is no longer 0 volts here, there's going to be some potential generated between them. Well, the one that ends up shifting is the voltage on the die. It increases, and it can increase to the point that your logic levels aren't really your logic levels anymore, right? Back in the day with TTL, we did like 1/3 and 2/3 of your source voltage. Well, what if this ground bounce is enough to shoot the 0 volt here up to 1 or 2 volts? Well, then your data signals don't really matter what they're doing anymore, because they're in some metastable state, some undefined logic level. The way that you get around this is by putting these tiny capacitors. We call them bypass capacitors, and they don't really look like they have enough, enough chutzpah to do anything useful. But what they can do is dramatically reduce the loop area. Right, you put these as close to the pads as you physically can. Still stay out of the courtyards, but just get those things really close in there and tie them in with vias if you need to, or however you want to connect these things to your ground layers. But get them as close as you can. You want to reduce that loop layer however you can, even if you have to put the capacitors on the bottom side of the board. But keep an eye out for loop areas and decrease them wherever you can. Now, I talked a minute ago about decreasing your yield when you're doing the broadside coupled. It can happen. One of the things you're responsible for as a designer is keeping an eye on cost. And what's that trade-off going to be for you? Is it going to be the fact that your yield goes down, but you can put more boards per panel? Okay, that might be a fine trade-off. Is it the fact that, yeah, you've made your board so very, very small now, but your yield's 30%? I mean, I would hope it would never be 30, but you kind of get the idea. Make sure that you're designing stuff that can be built with an acceptable yield. If you start getting into the weeds with these things, you know, here's our current process minimums. If you start getting into the weeds with these things and, you know, we tell you that we can do 3 mils safely and you're like, well, what do you think about 2.5? We can do that. We do it every day, but your yield's going to suffer. So how close do you really need to squeeze this stuff is a question that you've got to decide. One service that we do offer, and this is free for all comers. I mean, you can live in Tunisia and never order a board for us. We don't really care. It takes 30 seconds to do, but we can run some DFM checks for you that'll go through and it will find the minimum features on your board. So if there's any problems, you'll know them before you order a board from whoever you order it from, right? Again, this is a free service. You don't have to buy your board from us. So this particular one went through the board, and this is just one aspect of the DFM. And it identified that the minimum trace width is 8 mils. Okay, this board can, you know, this is like a 1/2 ounce copper board. This board can be built in any shop on the planet. There's no issues there. Now, if this person wanted this out of 4 ounce copper, we could still do it. 5 ounce, okay, we can still do it. 6 ounce, you're pushing it. Don't push it. See, when copper etches, it doesn't etch straight down from the mask. It kind of starts going in a little bit of a curve. And if you leave it in the etching tanks long enough, you kind of get this slightly curved trapezoid. You have to really, really over etch it to get purely vertical sides, and it's simply not worth it. But that's something we sometimes see high-speed designers want because that's what they modeled. You have to over etch, which means you need greater spaces in between the traces, which then costs you space at the very end. Excuse me for one moment. All right, we do have a question. Can you please re-explain the slide where you mentioned that an inner layer between the power and return path can be designed? Which rule? Oh, okay. You know, I don't think I explained, I don't think I talked about planar capacitors. I'm sorry about that. Thank you, Suresh. So one of the things that you can do as a designer are incorporate planar capacitors. Basically, you just put 2 sheets of copper with a very thin dielectric between them. Now, the capacitance is going to be picofarads per, you know, square inch or whatever it is. It's going to be ridiculously low, and you're going to look at it and you're going to say, what am I even bothering with? But what you're really doing is decreasing the loop inductance, right? You're giving another path for these things to take to get back without going all the way out to the power source and coming back. So if you can install, you know, physical MLCCs right near the part, or maybe create some out of the copper features themselves, what you're going to be doing is decreasing that loop size. You're going to be affecting this. So this DT doesn't hurt so bad. And again, what you're trying to do is keep the voltage of the die, those levels, from dereferencing from the rest of your board. I hope that helps. I hope that helps a little, Suresh. Excuse me. All right. So let's get back down to this. When we make your board, you know, and I'll talk about core and cap and foil here in a second. What I've got here in the middle with the blue and red is core material with some copper traces on it. And these are the same traces that we saw earlier. The way that this is made is some factory over in Japan, they get this fiberglass, they get the epoxy, they get the foil, and they laminate it all together. And they give us a copper clad sandwich. We take that sandwich and then we go and we etch the copper away, leaving your traces behind. These traces are going to be very, very flat and very well impedance controlled. You know, when when we get that core out. Then what we do is take some prepreg material, here shown in orange and yellow. It's just like the core material, except, you know, usually there's a lot more epoxy and a little less fiberglass. And we take some foil and we will epoxy all or press all of that stuff together. The epoxy's gonna, I forget, activate, congeal, but it's gonna harden and it's gonna stick the copper to the core material underneath. And then we can go through and we can etch your outer layers. What I was trying to tell you earlier is that when we do that, the broadside coupled ones have a little more chance for deformation, a little bit harder to control the impedance. The side coupled, it's a lot easier to make sure that whatever's happening to these two happens at the same time in reference to the outer copper player, because that's what's going to be controlling the impedance, the distance, and the prepreg, the material that's all inside here. One thing too that I forgot to mention, but it's worth noting, that if you look at where these coppers lie, depending on what materials that you have underneath, you can run into some troubles in that one of these traces can be over fiberglass mostly, and one of these traces can be over copper mostly. And the issue that you have with that is that you end up with different impedances as these things travel over. So what do you do about that? Well, if you're using regular glass, you can run your traces at about 22 degrees. And that way they're both undergoing transitions at a relatively known rate. If you have spread glass, you can run them at about 5 degrees. A little easier to route things with the 5 than the 22. You end up not wasting so much space. Now, whenever there is a change in impedance, a little bit of energy gets reflected. And depending on how big the change of impedance is going to affect how much energy is reflected back. And you can end up, if you're not careful, with these ringing, these oscillations in your lines. So what's happening here is a signal, you know, the trace underwent a transition, and the energy fields were created around the conductor. You know, everything traveled down the conductor till it got to a change in impedance. Then the energy had nowhere to go, so it started bouncing back. Hit the other end, you know, the gate had nowhere to go, started transferring back. Each time a little bit of energy is dissipated into the system. You get these ringing effects, and sometimes they can be quite pronounced. Even this is pretty pronounced. They probably should have put a damping resistor or something on there, either to slow the edge rate or something to better couple the transmission line. So looking at UTI. But you got to be careful when you're designing stuff, especially when you're doing prototypes. I do prototype stuff, and I want test pads absolutely everywhere. Okay, that's fine for low speed, but when you do high speed, all of a sudden now you've got a trace that's transitioning from 50 ohms, maybe into air, you know, now it's 377 ohms. It's going to reflect back hard, and a lot of energy is going to start bouncing back and forth. So keep an eye out for via stubs, keep an eye out for test points, keep an eye out if you're running, you know, buses that keep breaking off into T's at every, I've seen it, I don't do it myself. You never know when that stuff's going to happen. All right. A couple other things to keep in mind when you're doing designs. The artwork that you give us is not the artwork that gets made. We mess around with your stuff when we receive it. All fab houses do. And we'll cut back the copper in some spots. We'll compensate in others. And the reason is, like I said earlier, the copper doesn't etch straight down. So we've got to modify this stuff. So after the etching occurs, we've got your trace as close to spec as possible. And that means that we're going to be modifying some of your copper, especially on your impedance controlled stuff. So have a conversation with your fab house about what they're doing to your traces, because the stuff that you modeled in your whatever program might not be the stuff that's actually coming out of the other end. The more sophisticated field solvers, you know, take this into account, but some of the simpler ones, especially the online calculators and whatnot, they view everything as a rectangular or trapezoid, and it's too simplistic. You need something a little more sophisticated. Your board house should offer trace and space for whatever impedance that you want. They should be able to create a board stack for you. And it's another service that Royal and Advanced Assembly provide for their engineers. If you need a 50 ohm single-ended or a 110 ohm double-ended for let's say a USB, contact your board house. They'll say, okay, you're going to use these prepregs, it's going to be this thick, and you work back and forth with them at the very beginning of the design. That way you don't have to rework stuff later. Coming up with, as a new designer, figuring out which prepregs, which core materials to use, it can be completely overwhelming. The best thing to do is, again, talk to your board house and work on your stack together before you begin your design, because that's going to also depend on what layers that you're going to run your high-speed traces inside the board. If it's really high-speed stuff, you're going to want a spread glass, something where there's almost no space in between them. If you're trying to save money, you're going to probably try to figure out how to use an open weave, like the 1080 or the 106. These are high resin content fiberglass materials that are great for bonding layers together, but are a pain in the butt for signal integrity. Because every time that your trace transitions over one of these warps, one of these weaves, and goes into the places where there's no fiberglass and it's just epoxy, the impedance changes substantially. It's fine for short runs, but if you're doing, long runs, motherboards, type stuff where things go 6, 12, 18 inches long traces, oh man, you're going to be having a bad day. Something else to keep in mind too is the coupling distance for your return path. When I was a new designer, before I'd ever met Rick Hartley, I made the mistake of doing, something like signal on layer 1, let's call it power on layer 2, ground on layer 3, and then signal on layer 4. I don't know why my boards worked other than luck. It was bad. It was just a bad call. Make sure that your return path is coupled as close as physically possible to your signal. And if that means having mixed ground signal layers, then have mixed ground signal power layers. Make sure, though, that there is a uninterrupted return path for each one of your high-speed signals. And it needs to be as close as possible, right? So when I did my first designs that were just objectively wrong, and I had signal on layer 1 and ground on layer 3, okay, theoretically, my return had to couple through my power layer. Okay, so that simply doesn't happen. What it was likely doing, the signal was coupling through the power and causing ripples in my power supply. That's no good. So, I mean, there's a lot to keep track of, and I hate to, excuse me, I hate to overwhelm you, but be careful always of where those returns are happening. All right, we did have a question in the chat. I would ask you guys to ask those questions in the Q&A, but the question is, what's the typical difference between dielectric constant between the fiber and the resin? Various factors, but let's say the dielectric constant of the fiber is, call it 4.0, and the resin would be like 4.6. And I'm just making those numbers up off out of whole cloth. They're going to be in that order of magnitude, but they're not going to be those exact numbers. But it's a significant change. And doing all of those transitions, I mean, the traces are, that's an 8 mil trace is roughly as big as one of these fiber bundles. So if you happen to have it over a gap and your other trace is over the fiber bundle, they're going to be going at radically different speeds, the signals as they transfer down your board. Okay, your board designers cannot say place your traces over fiber bundles only. There's no way to have that level of precision. So just something to keep in mind. All right, next topic. And I know I'm doing lots of topics for you. I hope I'm not overwhelming you. Cap construction versus foil construction. So 2 ways that we make boards. One, we take those cores, you know, that we get from Japan, and we squish them together with prepreg in the middle. The other way, foil construction, we start off with one of those cores, and then we just keep adding prepreg foil, prepreg foil, prepreg foil in each lamination cycle. So what's the difference between them? Well, as fabricators, we always prefer foil construction wherever possible. As designers, especially if you're using some exotic materials, Rogers materials, PTFE, anything along those lines, you're going to probably want to buy the core with the foil already on it. And that's going to affect what kind of vias you can choose. It's going to affect your cost. It's going to affect a lot of things. Remember, we prefer sequential stack up, foil construction. But what can you do with each? Well, if you have the core layers, we can create pretty much any mechanical via in that stack. If you have the sequential stack up, we can start using micro vias, laser vias. And the nice thing about these is we can put them from any layer to any layer without creating via stubs that are going to stick out the other side and cause reflections. This would be an example of a via stub. Whether or not it was a problem, I couldn't tell you, but the through hole went on the bottom. So with the sequential stack up, again, we can connect any layer to any layer. With the core construction, we can connect some layers to other layers, but not every layer to every layer. So you kind of have to imagine how we're going to build that sandwich. And we can work with you on this, by the way, but you kind of have to imagine how we're going to build that sandwich and then go from there. Through hole vias are the cheapest mechanical via. Blind and buried vias can really affect your cost. So you want to try to avoid those whenever you can. But if you do the sequential stack up, like I said, we can connect any layer you want to any other layer that you want. Couple other things to keep in mind when you design your stack up, make sure that it's a balanced stack. This isn't a signal integrity issue as much as it is a assembly issue, right? The fabricators can build any stack you want, and we've got big presses that are really high pressure. We can flatten out anything that you want. But if your copper is not balanced, what happens is when we go to assembly and we put these things in the reflow ovens is they turn into potato chips. And we can't put flat components on curved boards. We got a process engineer over at Advanced Assembly, Sebastian, who will rant and rave at this for hours on end for you if you ever have questions regarding this. You might, from a signal integrity standpoint, want to create an unbalanced stack up, right? Keep your signal close to a return path and then do whatever you're doing over here far, far away. Okay, from a signal integrity issue, great idea. But from a design for manufacture, design for assembly issue, horrible idea. So with that, let's start addressing some questions. I know I did quite a few different little things rather than just hitting one topic. But I meant this to be more of an introduction than a complete overview. We're always available for questions. So what is the cost difference between mechanical through hole versus laser microvias? Roy, I don't know. I can tell you that a mechanical through hole is the cheapest via. We do those all day, every day. Those are in every single board that we make. Those are absolutely going to be cheaper to the extent that we don't even really cost them out unless you're doing something really crazy small. So laser, because it's an additional process, it's going to cost more. How much more? I don't really know. But if you want to send us your design files or just email sales and ask, they can give you a number. I don't work in sales, so I don't really have that for you. My apologies. Question is, with the sequential stack up, will that provide higher yields of the boards? And the answer is yes. It really comes down to registration. Well, it comes down to a few things. One, if you're doing sequential stack up, you can't etch interior layers after they've been laminated. You've got to etch them and then laminate them together. Well, one of the issues can be that, let's say you put these things in the high pressure press, And you can roll traces. You can cause traces to fall over if if the aspect ratio is off. Okay, your board's done. You know, we've got to throw the whole thing in the trash. Other issues are registration, right? The stuff that you send us isn't what we etch. We have to modify, stretch and shrink things in certain areas. And then we've got to get everything aligned when you squish it all together. It's really hard to do. So for cap construction, your yield is always going to go down. Foil construction, right? We can throw your board into an X-ray machine and we can visibly see what's happening on a lower layer so that we know that we're lined up on the layer above it. So we've got much more control over foil construction than we do with the cap. So I hope that helps. All right, what other questions do we have for you? Or do you have for me? It's crickets out there. Would anybody like to raise their hand and ask? We can do that too. We can allow people to talk if you're more comfortable doing that than typing. Did I completely overwhelm you with information? Was it just enough? All right. For those of you asking, how do you get a copy of the presentation? We will post this on our website within the next couple business days. It'll be either at aapcb/blog or royalcircuits.com/blog. All right. Now we're getting the questions in. They're all showing up at once. So Stanley asks, for today's circuits, what is considered high speed? It really has little to do with your, with actually the frequency of your circuit and more to do with your rise times, Stanley. So let's get that slide back up. And this is just a general rule of thumb, if the rise time in nanoseconds is greater than the length of your trace in inches, you've got high speed and you've got to deal with it. This is Dr. Eric Bogatin's rule. Now, realistically, you probably have another order of magnitude to play with, but I mean, I sure wouldn't do that without having access to some high frequency simulation software. Not because it can't be done, it just would be, I would be uncomfortable spending money to, you know, produce a panel if I wasn't sure. So I hope that helps. We're going to dismiss that one, but thank you. So the question from Dan, I think this might be related to another one that he asked, is, so it costs more, but I get the answer is where you are saving. Let me look at your other question real quick, Dan. Okay, so yes, so sequential stack up might cost a little bit more, although it would really depend on your design. That is our preferred construction method, so it might actually end up being cheaper. But if you have, you know, really small traces and everything, you might have a high risk design. It could very well be significantly cheaper to do a foil sequential stack up than a cap stack up. Really what you'd want to do is talk to sales, because I don't deal with money at all. And I really have, my only concerns are what makes good boards, you know, how to get better yields, how to get better performance out of your boards. I'm not really concerned at all about how much money you spend. I'm sorry, that's not really helpful. But email us at sales at either company and we'll get an answer for you, okay? How do you connect vias to the layers? So the way that vias are formed is we drill holes in the board, and then we put them through what's called a desmearing process, right? When you drill a mechanical hole in the board, or you do it with a laser, it leaves some debris behind. It smears the epoxy. So we go in there and we'll mechanically abrade that and get a nice clean hole where all that's there is, you know, clean, clear fiberglass, some epoxy, and then the copper. Then we'll put a electrolysis, what was it, nickel or palladium? I think we're just using nickel these days. But anyways, we put an electrolysis nickel deposit in there, and then we put in copper in a plating bath, right? We put your whole tank in a big vat of acid with these copper ingots on either side, and we connect it to a battery, and the copper ions leave the ingot, and then they travel to your board. We've made the insides of the holes conductive with that electrolysis nickel that we put in. So they start to plate with copper, and they start to connect electrically with those other, with the vias that are already there, the other layers of copper that are already there. We've actually got a VIA webinar where we talk about that, and I've got some graphics because, you know, talking about it doesn't really do it justice. If you check out our blog, you'll see, I think it's called All About Vias. All right, any other questions? All right, then. I do want to thank everybody for joining us. I hope you found it useful. And I know it was a lot. It was a lot of different things. I apologize for that, but I did kind of want to give you a few different ideas of things that you might not want to look out for. If you have additional questions, please email sales@royalcircuits.com or sales@aapcb.com, and we've got sales assistants there that will bounce your questions to the relevant department and follow up with that, whether that's engineering, whether that's me, or you can just email me directly and I'd be happy to take care of you there. With that, I would like to thank everybody for joining and listening to me go on and on and on for an hour. Royal Circuit Solutions and Advanced Assembly is happy to assist you with whatever you might possibly need. Again, free webinars. If you need engineering support, we offer free engineering, free everything. All you got to do is just reach out and ask, and we're happy to help. Visit us at royalcircuits.com/blog or aapcb/blog, and you can learn more. All right, with that, everyone, I want to thank you again and hope you have a wonderful day. I hope to talk to you through email. Bye. Stop. How do we stop?